Okay, so I'm going to take a look at some of the more important examples and definitions in section 2.1, which is matrix operations. The primary objective of this section is to learn to multiply matrices. So we've already discussed if I have an m by n matrix A, we can represent it a few ways. We can think of it as a series of column vectors. We can think of it as a two-dimensional array of entries. You see here A11, here's A1J. This is a double indexing where the first number indicates the row and the second number indicates the column. So for example, if I said A25 would refer to the entry in the second row, fifth column of the matrix. That's what's explained here, Aij, the ith row and jth column. The entries on the main diagonal would be A11, A22, A33. Some other definitions that make sense, somewhat obvious. The zero matrix refers to any matrix whose entries are all zero. A diagonal matrix is a square matrix where the non-diagonal entries are zero. A square matrix where the non-diagonal entries are zero. So straight down here I would have I could potentially have non-zero entries, but off of that main diagonal I would have zeros. This includes the identity matrix, which is going to be very important. The identity matrix, again, is a square matrix with ones on the main diagonal and zeros elsewhere. There's a lot of other definitions in here that kind of make sense that are really just extensions of the way you work with vectors, but now we're talking about a two-dimensional array of a matrix, how we add them, what it means for two matrices to be equal, some operations down here, and even some theorems. These are all pretty obvious. They're self-explanatory. You find things like the addition of two matrices is commutative, and if you have three matrices, we also have associativity of addition. Basic things that work how we would want them to. The bigger issue, as I said, is how we multiply two matrices. So let's suppose I have a matrix, an m by n matrix A, and an n by p matrix B. So when I multiply these, first off, the dimensions were given as m by n and n by p. In order to be able to multiply two matrices, these inner dimensions have to be the same. The number of columns in the matrix on the left has to equal the number of rows in the matrix on the right. The order is going to matter here. The product then of these two matrices will be m by p. So this is an essential step in understanding, can we multiply two matrices and what will that product look like? So, for example, if A is a 4 by 3 matrix and B is a 3 by 2 matrix, we want to know what are the sizes of AB and BA. Well, if I'm thinking about AB, that's a 4 by 3 matrix multiplied with a 3 by 2 matrix. The inner dimensions match up, so this would be a 4 by 2 matrix as the product. How about BA? Well, for BA, I would have a 3 by 2 matrix multiplied with a 4 by 3 matrix. The inner dimensions do not match up, so BA is not defined. Now, backtracking a little bit more to that definition, the product AB, the product of a matrix with another matrix, can be thought of a couple ways. One way is to think of it as the m by p matrix whose columns are the matrix on the left multiplied with the column vectors of the matrix on the right. So let's take a look at that. So this is one way that we could express this. AB, the same A and B that are on the example on the notes, are this matrix. This is the matrix B. So what is AB1? Well, AB1 is the matrix A times the first column vector of B. We know what's happening here. You're taking a linear combination of the columns of A. So I would take 2 times the first column of A, which would be 4, negative 2. 0 times the second column of A, that's going to be 0, 0. And 4 times the third column of A, so that is 24, 4. So if I combine those three vectors, what I have is 28, 2. Now I can do the same thing with AB2, taking a linear combination of the columns of A. So -3 times the first column will give me -6, 3. 1 times the second column, that's 3, 0. And -7 times the third column, that's -42, -7. And if I combine all those, that will be -45, -4. So then AB is, I take these two columns as the columns of AB. Now that worked out okay, but that might not work out so well if A were a larger matrix or if B has more columns. So really we need a better, more efficient method of doing this. This is not the traditional way of viewing matrix multiplication. So let's think about this. More efficient way of doing this. The matrix AB, the product of those two matrices. So this is defined if the I consider these matrices row by column. The dimensions of A are 3 by 2. The dimensions of B are 2 by, excuse me, I said that backwards. The dimensions of A are 2 by 3. The dimensions of B are 3 by 2. I can multiply those because the number of columns in A equals the number of rows in B. I'm always considering rows by columns, though. So here's the deal. Each entry in this product matrix, which I've labeled C, C11, C12, C21, C22, each entry of this product is a dot product of one of the rows of A with a column of B. Rows by columns, I will take rows of A to multiply with columns of B. It's a dot product. So for example, when I want C12, I will take the first row. This is the entry in the first row and second column of the matrix. I will multiply the first row of A with the second column of B and get that dot product. Once you understand the notion of a dot product, it makes it a much simpler way to look at matrix multiplication. So let's take a look at this. What will we get? I know I will have 4 entries because this is 2 by 3, this is 3 by 2, so I have 4 entries as we've already discussed. The first entry, I will multiply, since I am in the first row, first column, I will multiply the first row with the first column. 2 times 2 is 4, plus 3 times 0 is 0, plus 6 times 4 is 24. How about the first row and second column? Well, I will multiply the first row with the second column. I'll have -6 plus 3 minus 42. Now let's move down to the second row. Second row, first column, I multiply the second row with the first column. So I will have -1 times 2, 0 times 0, and 1 times 4. Then I will have -1 times -3, which is 3, 0 times 1, which is 0, and 1 times -7. What does this give me? 28, -45, 2, -4, which matches up with the result I got before. Once you get used to this process, this is a much, much more efficient way of computing the product of two matrices. Now, it's worth noting, in the notes right here, it works you through this step by step. I thought it would be easier to show you this live. That's why I actually worked out the problem on my own paper. It's worth noting that BA is also defined in this case. B is 3 by 2, and A is 2 by 3. So their product would be a 3 by 3 matrix. The inner dimensions match up, so this is a 3 by 3 matrix. I would be multiplying together smaller things because the rows of B have only 2 entries, so I'd be multiplying these rows by these columns if I did it in the opposite order. But I would also have to find 9 separate dot products to find the entries of my product matrix. So there's something very important about matrix multiplication which we want to introduce, which we want to see right here. So here I have CD, and I have the matrices C, D, and the vector E. I'm asked to find CD and DC. Now, since those are both 2 by 2, I can multiply it in either order. In both cases, I will get a 2 by 2 matrix. So if I'm multiplying this, what will I get? 1, 2 is going to be multiplied with 3, negative 1 to give me 3 minus 2. Hey, I guess I should put this on, right?
Sorry, Bobby.
No problem. So that guy just like did it.
How would we do that?
Sorry about that. All right, what was I doing? If I multiply these, I multiply 1, 2 with 3, negative 1. So that would give me 3 minus 2, which is 1. I multiply 1, 2 with 5, 4. That will give me 5 plus 8, which is 13. I multiply negative 2, 1 with 3, negative 1, which will give me negative 6 minus 1, which is negative 7. I multiply negative 2, 1 with 5, 4, which will give me negative 10 plus 4, which is negative 6. What if I do this in the opposite order? We're going to see right away that matrix multiplication. Okay, sorry about that. If I multiply these, I'm going to see almost immediately that matrix multiplication is not commutative. I'm not going to get the same matrix as I had above. So 3 times 1 is 3, 5 times negative 2 is negative 10. So that is negative 7. How about in the next position? 3, 5 multiplied with 2, 1 will give me 6 plus 5, which is 11. Negative 1, 4 multiplied with 1, negative 2 will give me negative 1, negative 8, which is negative 9 is their sum. Negative 1, 4 with 2, 1, I will have negative 2 plus 4, which is 2. Now we notice right away that CD does not equal DC. Very important that we understand that matrix multiplication is not commutative. How about ED? DE we can compute, that's simple. ED though, if we tried to compute AED, E is a 2 by 1 vector, D is a 2 by 2 matrix. And as we previously stated, since these inner dimensions do not match up, ED is not defined. Now, there are some properties of matrices that we have to concern ourselves with. Matrix multiplication is associative. Since we do not have commutativity, we will actually have both a left and a right distributive law. If I multiply a matrix by a scalar, scaling all the entries in the matrix, it doesn't matter if I multiply a product by a scalar or if I multiply either one of those matrices first by that scalar, I will get the same result. And the identity matrix is a multiplicative identity, meaning if I multiply a matrix on the left side or right side by the appropriately sized identity matrix, then I will get A itself. Now you notice here I have IM, I have IN, because these identity matrices, their dimensions depend on the dimensions of A. If A has M rows and N columns, well, on the left I have to multiply by something with M columns, an M by M identity matrix. On the right I would have to multiply by something with N rows to match up with the number of columns in A, so the N by N identity matrix. So in general, AB does not equal BA. We do not have commutativity. Cancellation laws do not hold for matrix multiplication. If AB equals AC, then it is not true in general that B equals C. If a product AB is the zero matrix, you cannot conclude in general that either A equals 0 or B equals 0. Both of those things kind of tie together. Proving this would also prove that statement 2 is also a fact. So let's look at some more examples here. In example 4, you're asked to find a non-zero matrix B such that AB equals 0. These numbers are simple enough that you could probably honestly just guess at it. If you're trying to think about the actual math of it, let's say B has the entries A, B, C, and D. Then the product AB is this: A plus 2C, B plus 2D, 2A plus 4C, 2B plus 4D. Now if I want each of those things to be 0, A plus 2C equals 0, 2A plus 4C equals 0. Well, both of those are true when when A equals negative 2 times C. Similarly, over here, B would have to equal negative 2 times D. So one such matrix where that is the case I can pick C and D to be whatever, 3 and negative 1. A has to be negative 2 times C. B has to be negative 2 times D. This would be one matrix, one of an infinite number of matrices that, when multiplied on the right by A, give me 0. So, since we're multiplying matrices, we can also talk about powers of matrices. If I have A to the K, that would just mean the product of K copies of the matrix A. Now, it's also worth noting that for this to even be defined, A necessarily must be a square matrix. Why? Well, we know that A times A is only defined if N and M, if those inner dimensions are equal. So N must equal M. Therefore, A is square. And you can compute that down here. 1, 0 multiplied with 1, 3 will give me 1. 1, 0 multiplied with 0, 2 gives me 0. 3, 2 multiplied with 1, 3 will give me 3 plus 6, or 9. 3, 2 multiplied with 0, 2 will give me 4. When I multiply these, I can see 1, 0 multiplied with 1, 3 will give me 1. 1, 0 multiplied with 0, 2 will give me 0. 9, 4 multiplied with 1, 3 will be 9 plus 12, or 21. 9, 4 multiplied with 0, 2 will give me 0 plus 8, or 8. So that is the essence of matrix multiplication. There is one other thing in this section that we do need to note, and that is called the transpose of a matrix. This does have applications somewhere down the line, but it won't be immediately obvious why we're doing any of this, why it's helpful, although it will allow us to understand some different things about matrices as we proceed. So if I give you an m by n matrix A, the transpose is going to take all of the columns of A and make them rows. And all of the rows then become columns. So the A transpose, denoted A with a superscript of T, the first row, 1, 2, 3, 4, becomes the first column, 1, 2, 3, 4. The second row becomes the second column. The third row becomes the third column. Again, why this is useful will not come up for some time, but it is something that we do need to understand about matrices. There are some properties. The transpose of a transpose gives me back the original matrix. If I want to take the transpose of a sum, that's the same as taking the sum of a transpose. If I were to scale a matrix by some scalar and then transpose it, that would be the same as if I scaled the transpose. And less obviously, the product of two matrices, if I transpose their product, that is the same as multiplying the transposes in the reverse order. AB transpose is equal to B transpose multiplied with A transpose. There are some examples in here just to drive home multiplying AB and making transpose. So if you do AB with and then transpose it, AB 1, 2, 0, 3, 0, 1, 1, 0, negative 2, 2, 1, 4. When I multiply these, I will have a 2 by 2 matrix. 1, 2, 0 multiplied with 1, 0, negative 2 is 1 plus 0 plus 0, 1. 1, 2, 0 multiplied with 2, 1, 4 is 2 plus 2 plus 0, so 4. 3, 0, 1 multiplied with 1, 0, negative 2 is 3 minus 2, or 1. 3, 0, 1 multiplied with 2, 1, 4 is 6 plus 4, or 10. So then AB transpose, the first column becomes the first row, so on. Can do some more with this. A transpose B transpose will actually turn out to not be defined because the dimensions of A are 2 by 3, so A transpose is 3 by 2. The dimensions of B are 3 by 2, so that will be 2 by 3. I don't know why I said it was undefined. Clearly I was thinking of a different example. That can definitely be done. But I will leave that to you. There's a little proof down here. I'll do this as I close. I want to prove that the transpose of ABC is actually the product of all three transposed matrices in the reverse order. And how I can do this is using the theorem that I had above. If I view this as AB multiplied with C, then I know that the transpose, based on that third property, this will be C transpose multiplied with AB transpose. But the other thing we know is that the product AB transpose is the same as the product of the transposes in the opposite order, thus completing